Everyone, and thanks to the organizer for giving me this opportunity to present my talk here. And I don't want to, be a hindrance between you and your coffee, so I will try to finish it quickly or as soon as it takes. So I will talk about boundary terms in gravitational action. So as Krishna already pointed out, this is actually the thesis work of Krishna, but we tried to switch it over, and I want to work on, talk on boundary terms while he talked on thermodynamics. So let us see how it goes. So let us start with a brief outline of the talk. So at first I will talk about a very brief introduction to action principle in both classical mechanics as well as in field theory, classical field theory. Then I will talk about action principle for relativity and as well as its related complications. Boundary terms, I will discuss what it is, what I meant by boundary term for Einstein-Hilbert action in relation to null and non-null surfaces. And finally a brief introduction to boundary terms for Lovelock gravity. So these are the main references. So this whole lot of work started from the work by Paddy, which published in MPLA, and after that we build up on the particular work. So this is Krishna, Bibhash, and Paddy, of course. So we all are involved in this particular project. So let us start with variational principle in classical mechanics. So you have a mechanical system and you characterize it by a Lagrangian, which is a function of generalized coordinate and generalized velocity, q and q dot. And at two instants of time, say at t1 and t2, you fix your coordinates, q at t1, q at t2, and you can vary the path in between. So how you get the field equation? So you start with an action, which is essentially the Lagrangian, integrated from t1 to t2. Then what you do? You vary the path. So you change the trajectory from qi to qi plus delta qi, and ask how the action changes. So there are two terms to the action. The first term is a boundary term. It depends on the values of this object at t1 and t2. And the second term is a bulk term, that is, it depends on the integral, and this is your famous Euler-Lagrange equation of motion. Now, in order to get Euler-Lagrange equation of motion, which you want to set this term to 0. So how can you set this to 0? Now, you said that at t equal to t1 and t equal to t2, I have already fixed my coordinate. Therefore, there is no change in the coordinate at the two endpoints. And then you get back this equation. Now, here you have to be a bit careful. So essentially, you are solving a differential equation here. Now your Lagrangian depends on q and q dot, so therefore this one depends on q dot. So you are acting one more time derivative, so it depends on q double dot. So this is a second order differential equation in q, and in principle when you solve a second order differential equation, you expect to use two unknown constants. And those are the two unknown constants which is essentially compensating for this delta qi. So therefore your variational principle is well posed. If you put these conditions at the boundary, this equation will have some unique solution. But there are two crucial facts. So one I already mentioned, that you have to be very careful about the boundary condition. The other point is you can actually get the conjugate momentum from the action principle itself. So essentially this particular term which is sitting here, del L upon del Qi dot, is your momentum. So therefore a variational principle not only gives you the equation of motion, it also gives you the momentum conjugate to the particular variable. And you have to be careful about the boundary condition. So let us see how it comes about. So we all know that addition of total derivative is completely harmless to an action principle. Your field equation don't change. But I am going to show you that addition of total derivative is very much harmful to action principle. Your action principle can become ill-defined. So let us start with the most simple Lagrangian you have, a free particle in one dimension. So it is just half q dot square. And you add a total derivative term which is half q dot. And what you end up getting is an action which depends on double derivative of q. Well, so and good. Let us go and vary the action. The same thing, you change q to q plus delta q. So when you vary the action, you get a plethora of terms. So this is your well-known thing, q double dot equal to 0, which your free particle action should give, equation of motion. But then on the boundary term, you are in trouble. You have to fix q, you have to fix q dot at both endpoints. Now how would you do that? You have a second order differential equation, q double dot equal to 0, whose solution is q equal to at plus b. So you have a and b as two unknown parameters in your theory. So you can only have two boundary conditions, but you are essentially fixing four boundary conditions. So therefore your boundary data and your equation of motion are completely inconsistent. So therefore even if you add a total derivative term which did not affect your equation of motion, your action principle is well posed. You can't do anything with this action. Therefore you have to be very careful about what you do. So this requires, and actually for most choices of boundary data, you won't have any solution. So the variational problem as presented by this action, which is half q double dot, is actually a ill-posed boundary value problem. And thus, given such an action, you have higher derivative terms, and they cause problems. So this also gives you another instance. Suppose I have given you this action. You would say, well, it is well ill-posed, so what would I do with it? So you can do something very similar. You can say, well, let me add a total derivative term, and then I have a well-posed action principle. So this actually gives you two things. One, addition of total derivative is not always a very simple thing to work with. And second, if you have a ill-posed action, you can actually add total derivatives to make it well-posed. And this is exactly what happens for GR, which I am going to discuss.
Sumanta, you can't have arbitrary total derivatives, right? In that action, you can add only total derivatives which are functions of Q.
Yes. Yeah, I agree. No, not Q, I mean, I can add this as a total derivative, right, which is a function of Q and Q dot. Yes. Okay. So before I go to that, let me introduce the space-time volume. So you have a 4-dimensional space-time. In that, you choose 2 time slices. So you have some t equal to tf, final time slice, and some t equal to ti, initial time slice. And then you have a spatial volume, which is like a cylinder here. And you take the cylinder to infinity at x equal to a large distance, so that there are no contribution on the boundary coming from the cylinder, these endpoints. So you only have contribution coming from the t equal to tf and t equal to ti, these 2 points. Then I go to electrodynamics with this setup in 4-dimensional space-time. So electrodynamics is a vector field theory. So you have a 4-vector AI here, and the action for the vector field is essentially the FAB, the standard electrodynamics action, where FAB is dA of AB minus dB of A. And FAB is antisymmetric tensor field, and information of both electric and magnetic field are contained in it. It has 6 independent components. So now we do the same thing. You vary the vector field, that is AI going to AI plus delta AI. So it causes a variation of the action, which gives you the Maxwell's equation, which is derivative of Fik, and then you have again a boundary term. So this boundary term depends on the normal to the surface as well as the variation of AI. So what you say, you will fix the variation of AI at the boundary. So let us suppose you take that, then you have your Maxwell's equation. Now as I told you, you always assume that the spatial boundary is at infinity. Therefore, there is no contribution coming from this term nk when it is non-zero. That is, n alpha has no contribution. At spatial infinity, things are dying out. So therefore, the only contribution will come from the time surfaces. So then your nk will have only 0 value. So it is f0 I. And since Fik is antisymmetric, this will translate into f0 alpha delta A alpha. And f0 alpha is nothing but the electric field of the electric field. So it turns out to E dot delta A. Therefore, what it shows you is that you don't have to fix all the components of the vector potential. You only have to fix the vector part of the vector potential, and the conjugate momenta to it is essentially the electric field. So just like in the case of classical mechanics, you can get the conjugate momenta. Here also you can get the corresponding electric field as the conjugate momenta to your vector potential. Let me now come to GR. So in GR I will start with the most simplest action, which is the Ricci scalar. So the first instance you will see that the Ricci scalar is not a function of G and its first derivative. It also depends on second derivatives of the metric. So the Ricci scalar is essentially structurally similar to our half QQ double dot action. It involves double derivatives of the metric. Now this is very peculiar, because if someone asks that you have to construct a very complicated action principle in classical mechanics, you will say I will construct a very complicated potential, I will put Q dot to the 4 or something, but you rarely come up with a Q double dot or Q triple dot terms. But the most simple action for GR has a double derivative of metric. Now you can't avoid it because this comes from equivalence principle, which says you can always go to a frame where first derivative of the metric vanishes and G is eta AB. So therefore, if you have chosen an action which just depends on G and del G, you could have made it vanish in any frame of reference. So therefore, you need this second derivative which incorporates the curvature tensor into picture. So then the problem starts. That is, you vary the gravitational action. So just like your half QQ double dot action is completely ill-posed, this action R root minus G is also ill-posed. Why? Now you do the same thing. You vary the metric, change GAB to GAB plus delta GAB. You get your Einstein's equation, of course, RAB minus half RGAB. Then you have a term which depends on this, which has a contraction with Na, and then there are other boundary terms with delta GAB. Those are fine. But let us take this particular term. This term is okay, but when you consider the second term, you see it depends on the normal derivatives of the metric, because there is a Na delay of delta GBC. So this is the problematic part. So just like you cannot fix both Q and Q dot at the boundary when your equation of motion is second order, similarly you are not supposed to fix the normal components of the metric because the Einstein equation is second order in the metric. So therefore your Einstein's equation and the boundary data you pose by this are not well posed, is not consistent with each other. So therefore the boundary term involves 3 variations: delta GAB, its projection on the hypersurface, and the normal derivative term. Now delta GAB equal to 0 gives vanishing of tangential components, but the normal components you cannot fix, and the field equations are therefore not consistent with it. So the action of gravity with Ricci scalar is not consistent, is a ill-posed problem, and field equation, that is Einstein's field equations, are not consistent with boundary data. So what should we do about it? So let us talk about various possibilities. Now incidentally, the first possibility came from Einstein himself. So he suggested, well, you have R. So what is the structure of R? The structure of R is del gamma plus gamma square. So it's a gamma square term and a derivative of gamma. So what you can say, let us take gamma square as my action. And then I have a del gamma, so which is a total derivative. So let us subtract off the total derivative. You can actually show that if you take gamma square Lagrangian as your basic variable, you get the correct field equations and your boundary value action is well posed. But that is not good because gamma square is not a covariant object. People love covariance. So then the first proposal essentially come from Gibbons and Hawking and also York, who suggested that you should add to Einstein-Hilbert action a term which is 2k root h. But that derivation is not a consistent derivation. So what the derivation we want is I have given you an action principle. You should vary it and get me everything you can do about this. So this is the basic idea which actually Paddy proposed in his MPLA paper. So I have given you an action. If you vary it, what are the things you are supposed to get? Of course, you will get an equation of motion term, which is the Einstein equation, say for example, or Euler-Lagrange equation. Then there would be a variation of the dynamical variable. There would be one more term which would give you a conjugate momentum and variation of the variables you want to fix on the surface. For example, in the case of electrodynamics, this would have been the Maxwell's equation, and this would have been the electric field, and this is the vector potential. Then there would be a boundary term, so this is the crucial thing, and then there would be a total divergence term. Now total divergence term is fine, you don't bother about them. But this is the term which is problematic. So how do you regularize it? Very simple. You just construct a new action. So you say, I will take the old action and subtract from it this boundary term and take a variation of it. So this will give you the same equation of motion because this is again a total divergence term. This is a delta dynamical variable. So everything goes through, just that the action now become well posed. So you fix the variables here with the conjugate momentum, you get the equation of motion and from the dynamical variable. Therefore everything is fine. So the point is, can we do it for gravity or for the r root minus g? So therefore what we expect, you have a d4x root minus gr as your Einstein-Hilbert action. You subtract from it this boundary term q. And when you subtract it and you vary the action, you get Einstein's equation GAB delta GAB. You get a total derivative term here, and you get some term XAB delta GAB. So what the structure of this term, I will be coming later, but this is what we expect to happen. So what we have to do, we have to identify this term q, we have to identify this term XAB, what they are for gravity. So this is what Paddy did in this MPLA paper. So he started with the variation of Einstein-Hilbert action with VA being the normal, and then you manipulate the terms. What you get at the end is a total derivative term, then you have a variation of 2 nabla A of VA, then you have some tensor here and delta Gij. Now if you are familiar with the extrinsic geometry of the surface, you will know that this particular quantity is essentially the extrinsic curvature of the surface. So if you have a normal vector, you can always compute this component di Vj minus this epsilon dictates whether V square is +1 or -1, that is whether the surface is space-like or time-like, and A is the acceleration corresponding to Vi. And you can exactly see this is the term which is sitting here, and if you take the trace of it, since V dot A is 0, that is acceleration with its corresponding velocities dot product is 0, you essentially end up this to be k. So the structure that you get is that the total term that appears at the surface to be a total derivative term, delta of 2k root h, then k hij minus kij delta hij. So this is essentially what Gibbons and Hawking did. They add this term 2k root h to the Einstein-Hilbert action to make it well posed. Now it gives you one more thing. So in electrodynamics, you see the 4 components of vector potential you did not have to fix. You only fix the 3 components of it. Here also you never had to fix the full Gij. What you have to fix is only the induced metric of the surface Hij, which has 6 degrees of freedom. And this comes as the conjugate momentum to it. Therefore in the case of gravity as well, you get this term q, which is essentially the term you have to add to the action, and the term conjugate momentum and what you have to fix. So I have not put anything from the outside. It's the action principle itself which leads me to this. Therefore I did not have to assume any symmetry, any particular space-time. This will work for any general case. But then there is one particular problem with it. That is, there is no generalization to null surfaces. So all the calculations that I showed you are only works for space-like and time-like surfaces. Now null vectors are very unique. Now the vectors are not null because they are like 0, 0, 0. It's null because they are non-vanishes. So a simple example could be the x plus minus t surfaces in your Minkowski spacetime. Now why it does not work, that I will come to, but they were not known before some time ago. So the reason is that on the null surface, the induced metric that we defined, Hij, they become degenerate. And actually its determinant is 0 or diverges. And similarly, the extrinsic curvature, the k, all the things that you compute, they are pathological. So you cannot go working directly that I have some object, I will just put these vectors and compute it. You can't do it that way. You have to be more careful. So for that, the result derived earlier, you cannot apply to null surface, and again you have to start from the first principle. So I won't go into the details of it, so you can find it in this paper with Krishna and Paddy and Bivas Maji, but I will state you the result. So here also you get exactly similar structure. So you start with the term B, which is essentially the surface term. It goes to a total derivative term as we expected. Then again you see there is a term delta of root q theta plus kappa. I will explain them in detail. Then you have a term which is theta AB minus theta plus kappa QAB. So it's exactly what I want. And then there is one more piece. So the total derivative term is fine. Now what is theta? Just like k was nabla of VA, theta is essentially the expansion of the null generator. So you have a null vector LA and the expansion of it is essentially theta, and kappa is the surface gravity of it, or in other words, the non-affinity parameter. And root q is the induced metric on the null surface. So this vector L Krishna has already introduced, and the vector k also he has introduced as that L dot k is equal to minus 1. So what should you do now? So what should you do for the null surfaces? To the Ricci scalar, you should add a term which is 2 root q theta plus kappa, and then your action principle would become well posed. So with this modified action, you would vary and you will get a total derivative term and two additional terms. One term would correspond to this delta QAB, which is essentially the metric that you have taken on the null surface, and the other term would be this delta LC. So why this additional term? So you can count the degrees of freedom. So QAB is a 2 by 2 symmetric metric, so it has 3 degrees of freedom. And delta LC, since it satisfies the constraint that it has to be null, that is delta L square equal to 0, this has 3 degrees of freedom. So in total 6, and also in the case of space-like surfaces, delta Hij had 6 degrees of freedom. So counting wise, everything is fine. So this essentially gives you the conjugate momenta to QAB, and this essentially gives you the conjugate momenta to LC. So in null surfaces, the null vector itself enters into the dynamics. So here again, the full structure of the theory gives you the corresponding boundary term. Here also we have not given any additional input, rather than we started from the Einstein-Hilbert action, varied, and the action itself tells me what I have to add to it. Okay, in addition we have to fix this. Now this was for GR. So last few slides I will just talk about Lovelock action. So what does Lovelock action means? So Einstein-Hilbert is fine, but people always thought, well, is that the only thing that I can do, or I can generalize or add to the Einstein-Hilbert action more terms? Now it turns out it's quite difficult. You can add terms like R square, RAB, RAB, RABCD, RABCD, and so on as much as you like, but the problem is the field equations contains higher order derivatives. And whenever your gravitational field equations become more than second derivatives, then it involves ghost, some kind which is known as the Ostrogatsky instability. So in order to avoid that, you want to bring the gravitational field equations to contain only second derivatives of the metric, and the only Lagrangian containing higher curvature terms that gives you second order equations are the Lovelock field equations. So what it contains? So this is the structure. It's essentially a summation of various Lovelock. So for example, if you take m equal to 1, it will give you Einstein-Hilbert. So let us see how it goes. So you take m equal to 1. So these are essentially curvature tensors. So for m equal to 1, essentially this PABCD would be just delta of ABCD. Now what is delta of ABCD? Delta of ABCD is essentially this particular object. So if you actually multiply this object, which is this, to RABCD, the first term will give you a R, second term will give you a minus R, so in total they will give you 2R, and so you will have your Einstein-Hilbert action. But when you add higher terms, it is more complicated to compute. For example, if you are in Gauss-Bonnet, a single term in here would contribute, so it would be 2 RABCD contracted with this particular tensor. So it will have a structure like R square minus 4 RAB plus RABCD. And you can go on with it. So the Gauss-Bonnet structure I have already written. So essentially for mth order Lovelock, this contains m number of RABCD, and then you contract it with this completely antisymmetric tensor delta. So the question is the formalism we developed for GR, whether it applies to this case as well. Now, I will show you the result only for Gauss-Bonnet because in general it is quite difficult, and if you want you can look up this paper which just appeared previous Friday. So, the variation, so the surface variation term, it involves a total divergence as usual. There is a conjugate momentum and then there is a variation of the variable. So, essentially here also it is Hij you want to fix. But then the counter term changes completely. What it depends on? It depends on some weird factors like 4th third, 8th third and so on. It depends on k cube, that is 3 number of extrinsic curvature contracted in various ways, and also depends on the d minus 1 dimension. So, if you do it in d dimension, this depends on the lower dimensional RAB. So, the essential idea of what we approached is that you start with the surface variation, use the Gauss-Kodasi relation which relates curvature in d dimension to curvatures in d minus 1 dimension and try to write various things manipulating them. So, here also you see the same structure is emerging. You start with the Gauss-Bonnet Lagrangian, you get a total divergence term, a conjugate momentum, delta of variables to be fixed and a delta of something in total. So, therefore, a similar calculation would also give you Lovelock, but I do not think that will fit this particular page. So, therefore, I will summarize now. So, we have elaborated the associated complications with gravitational action principle, that is you cannot just go away with saying R root minus G is my gravitational action, you have to be very careful while stating that. So, what resolutions, what things can you do to make it well posed are also discussed, and more importantly all these things come from the action itself, we did not have to introduce anything from outside. For non-null boundaries, we get the 2k root h expression exactly, and you know what are the degrees of freedom to be fixed, and also the same thing with null surfaces were identified, and what are the problems and possible resolutions. And finally, the corresponding situation for Lovelock gravity, that is for Lovelock also the conjugate momenta, the boundary term, what you have to fix, all of them have been investigated. So, with this, I thank all of you for attending.
One small thing I did not understand.
Okay.
When you're doing the general thing to change the variational principle, not the last things, but the earlier on,
Okay.
do you always encounter, I mean, is your surface, does it always encounter the light cone? And are you therefore having to use the formalism that allows you a null surface, or do you not normally encounter that?
No, so the situation with null surfaces you are asking, whether do we encounter that normally?
Do you always encounter a null surface, or is that just a special case?
Yeah, so the point is you don't normally encounter it, but the most cases you encounter, suppose you are interested in variational principle where your one surface is black hole event horizon and other surface is cosmological event horizon. Say you are interested in de Sitter Schwarzschild, then it would be very important there to know what you have to add to the action. Yeah. So I think.
We had a quick break.